3, 2.
All right, hello. We're doing the Advanced Hardware Design Project presentation. I'm Patrick, and I'll be walking you through our design of the Risc V processor. So over here we have a complete design data pad of the processor that we designed. And the main things to point out is that we're using the Harvard architecture for our design, which means we have a separate instruction and data memory. Other important components that we have in our Risc V processor are the control unit, which controls all of the control signals that we have in our processor, the ALU, which performs the arithmetic register file, the instruction data memory, which I mentioned before, and there's a plethora of immediate registers, including the program counter register. It should be noted that this is a multi-cycled computer, so as a result, every instruction takes a certain number of cycles to do, and this is the reason why we have more than a simple register. We have a plethora of registers to support multi-cycle functionality. Speaking of multi-cycle functionality, here is a finite state machine diagram for the multi-stage processor that we have. We don't have any arrows pointing because the diagram will be very messy, but it's a 5-stage pipeline. Sorry, not a pipeline, it's a 5-stage processor. So in the first stage, which is the IF state, we only have one. Every single instruction always starts at IF initialize. Then we have a certain amount of ID states, and these are broken down depending on what the opcode is for each instruction, R type, I type, etc. Execute states, these will depend on what operation the ALU needs to do in order to execute the instruction. So we have add, sub, SL all the way down. Mem states, these are used specifically for load and store word. And we also have write back states. So this is in order for you to write back into the register file. And we can also see this is just a big table of how all of the different states are for the different instructions. Main thing to point out is that some instructions take 2 cycles. Those are primarily the J-type and U-type instructions that we have. They only account for the IF and ID states and skip over execute, mem, and state and write. The only instructions actually that do take 5 stages to complete are the load instructions. Every other instruction that we haven't mentioned only take 4 cycles, where you skip the mem stage and go directly into the write back stage. And I should mention also we have eCall and eBreak. Those only take 1 cycle to complete. Okay, great. So now let's go over some simulation test benches. So this program right here is just a sample test case for multiplication. And I'm not going to go through the entire code, but if you do actually take a look at this assembly code, you will see that we are multiplying 6 by 3, and then the result should be 18. And we can actually calculate the amount of time it takes for this assembly code to run using our FSM state timing diagrams we showed in the previous slides. And if you do the work, you find out that it is 65 cycles that is taken in order to complete this code. Keep in mind this multiplication this algorithm takes O of n block time to complete. So because our second operand is 3, this loop that we have over here, which actually does the execution, has to re-execute 3 times, so that's being taken into account in our calculation. Okay, so if we just take a look at the start of the timing diagram for multiplication, you can see that the current state at which our state table is operating at is being incremented, and you can see how at the start we have LEY, and then that takes 2 cycles. 0, 0 is our initial state. Then we have another 5 cycles for the load word. 1, 2, 3, 4, 5, and if we keep going into the simulation, you will see that it does execute. If we jump straight into the end of the actual simulation, we'll see that the output is 0012, which translates to decimal 18, which means that the multiplication algorithm is working. Fibonacci, you want to do it? So with Fibonacci, this is just another test case that we have. This algorithm just executes the n-2 number of the Fibonacci sequence. So here we're putting in the number 6, so we should get the 6th element over here. So this should be the number 21 over here. And if you do actually take a look at how long this algorithm takes, and you do the calculations from the FSM diagram, you'll get 152 cycles. And then we take a look at this timing diagram, and you can see that yes, indeed, we do get 0 hex 15 over here at the output, which translates to decimal 21. All right, cool. So now let's move on to performance and area analysis. We should note that the clock speed that for our processor is 50 megahertz. We ran into some problems with timing analysis, so we couldn't quite get it to 100 megahertz, but 50 megahertz is still a pretty respectable number. When we looked at post-implementation results, we got that the total power consumption is 0.072 watts. 97% of that is static power, it should be noted. And then we also took a look at our hardware utilization. So the slice lookup tables are like 6.22%. We found that our FPGA was mostly underutilized with the exception of maybe the block RAM tiles. We used 64% of the block RAM available on our FPGA. Other than that, most of the hardware was underutilized, so we could definitely have more room to expand our processor if we wanted to in the future. High-level test cases. So over here, we actually were able to successfully get C code, and we were able to convert it into assembly code. And we ran some test cases, as you can see over here. So the factorial code, this just takes in an input from the switches of our FPGA, and then it computes the factorial of it. And do we not have a video? All right, and then we also have RC5 high-level test case. So we were actually able to get the RC5 working, and with this algorithm, what we ended up doing was we took an encrypted RC5 code, then we decrypted it, and if we printed out the message of FF on our FPGA, that would mean that the decryption would bring us back to the original input for our encryption. If we got a different output, we would print the output EE. So if you got FF, that means our processor was working correctly. If we got EE, something went wrong. And when we ran a test case, a high-level timing diagram for this, we actually did get FF after a very long period of time, which meant that our simulation was in fact working correctly. Future improvements and optimizations. So big thing that we want to do in order to improve our processor is to increase our clock frequency from 50 megahertz to 100 megahertz. Effectively, that will allow the processor speed to double. We do expect the power of the processor to increase as a result of that, but keep in mind that based off of analysis that we did, most of the power is static, and usually when we increase frequency, it's usually dynamic power that actually gets impacted. So we don't expect the power consumption to double. It should increase, but not by much. Another thing we wanted to do is pipeline our processor. Since we already have a multi-cycle computer, it's very easy for us to pipeline our processor. We might need to add a few extra registers. A couple of interesting things. We did mention that in our processor, every instruction takes 4 cycles. Most instructions take 4 cycles to complete. We do need to be careful when we do pipeline it that it doesn't interfere with the load instructions. Otherwise, we would have structural hazards. As well as we would need to implement some extra logic, such as forwarding logic, to handle other hazards that we have in our processor. And that's our presentation. Thank you for listening.